He'll soften up as he grows. Okay, so any questions, concerns, comments? So bring me your midterm if you got that integral question wrong on the true-false. The one that's like integrate 0 to 2 pi of cos theta dx. So we were talking about this yesterday. I actually got tricked by my own trick. Yes, interesting. So I must be very good at creating a tricky question. The answer was false. I can't remember what the answer is. Okay, so let's begin. So this is where stuff's going to start getting pretty serious, right? Because yesterday was the sort of just prep for this. Infinite series. Okay, so a series, infinite or finite, is a sum of numbers. So we've already sort of done these, right? When we showed you the sigma notation, that's notation for series. So here's the sum. So here's a series. We can have a series that's a0 plus a1 plus a2 and so on through an, right? With each ai a real number. So these individual terms here, summons, you could identify a0, a1, a2 as a sequence. So we can take a sequence of numbers and we can convert it into a series simply by adding the sequence. We can have infinite series. Those are ones that just sort of add on forever. And these are going to be of great interest to us. We can also have something called the partial sum. So you're going to have to, I'm just sort of defining notation we're going to need for today. So we use the term S to denote a sum. And if it's a partial sum, we usually just put an index there. And this indicates that you should take the sum from A1 all the way through AK. The infinite sum then is given by S without an index, which is equal to the limit as k goes to infinity of the partial sums, which we write like this. Right? K goes from 0 to infinity of AK. Now, I need to give you a warning about these type of problems. Depending on what we're modeling, it sometimes makes sense to start from 0, and other times it makes sense to start from 1. You have to be very careful about this bottom index, because it's going to be 0 or 1, and you're going to have to account for it. So it's a very typical mistake to make in these cases is to be off by one term, the first one. Right? So be very, very careful about what is down there. Keep aware that that can change. Okay, so we are interested in two things with these sums. Okay? Convergence, divergence behavior. It's not really that obvious if you can take an infinite amount of numbers and add them together and get something that's finite. Right? As it wasn't sort of very obvious that something with an infinite perimeter could bound a finite area. But suffice it to say these infinite sums can be finite. And then in that case, we're going to be interested in looking at sums and designating those sums as either being divergent or convergent. So that's the first thing that we're interested in. The second thing that we're interested in is something that I call a closed form. The closed form is kind of a nebulous term, but something like this, k to n of n, you can't really work with this. It's like saying, what's the integral of f? And you say, it's the integral of f. Like, that's technically correct, but I can't manipulate that at all. This is the sum of the first n numbers, which is a perfectly valid mathematical thing to say. Mathematics is indifferent to the fact that it was written like this. We can just treat it like a number. But for us, it's much more useful to have this. No? Right, what would you rather be given if I gave you 1,000,000? Would you rather add up the first 1,000,000 numbers by hand or use this? Okay, so this is called the closed form. Right? We'd obviously have preferences to have this. The problem is most sums don't have a closed form. Right? We generally do not have any way of figuring out some equation to tell us what the sums are. Right? It basically is dependent on our ability to deduce the pattern. Okay, so we don't normally have these closed forms, but for the time being, let's try to find the closed forms that we can find. There's like a bunch of categories for which we can actually attack, but it's usually the case, right? Because normally you can just put any function in here of arbitrary sophistication, and it's going to be hopeless to try to extract some pattern from that. Okay, so here's something I want you to think about while I wipe the board. So we're going to investigate our first infinite series. I'm going to start it from 1, all right, just to keep us on our toes. And it's going to be the sum 1 over 2k, right, or a half plus a quarter plus an eighth, and so on. Is it convergent or divergent? See if you can't come up with some type of argument to convince me either way. And can I wipe down the left board? Yep. I'll make one lap. Where's your working? Here. Too busy chatting.
Do you want to hear our idea? What's your idea? Let's convergence. Because 2 to the power of infinity, let's say, it's just going to keep getting smaller. So it's going to approach 11.
1 plus a half plus a third plus a quarter plus a fifth is divergent. So that's an example of something where the numbers are trending to 0, where the sum is nonetheless still divergent. So you may be correct, but your explanation is not sufficient, right? Because that is not enough to go to 0.
So if you have, you provide an argument for that, then the next one will be half of that half. The next one will be half of half of that. So if you can do that, it'll all add up.
Yeah, that's correct. I'm just curious what your intuition was.
They will, it's very good. They'll add up to 1. There is no approach 1. They'll approach 1.
That's the hard part. That's math.
Yeah.
You are correct. But in math, that's the well, your explanation is better.
Yeah, because you said it's an infinite.
Otherwise, why should I believe it?
Yeah, it is approaching. I'll show you. But again, what he said, do that. I don't know. It's wrong. It's one of
Try drawing a unit square.
as they said.
Okay, this is convergence.
Draw a unit square. We can take this one.
Way too
Draw a line through the middle.
Show us convergence. Convergence is approaching right at half. So why would it?
Think of the function.
What are the terms?
It's also half the
You're going to fill in the square.
Well, the function of the is
Going on in this country, I have to read right now.
So they have functions looking like that, but adding, so it'll go up from 1.
So how much? Yeah, it's like
It'll go like that, up to 1.
to like 0. So we want in the limit.
It'll go to 0. Thereby, it'll square.
No, that one would be the function of the sum, but the sum would be like that.
Yeah.
Because these will all add to 1.
Okay, so why is it not halfway? Halfway again.
Divergence is no, like, yeah, and then go to like infinity, like if you keep
Okay, that was x to the power of k.
not x by base,
They're always after
Okay, anyone have any guesses? Divergent or convergent? At least take the 50-50 guess.
Convergence.
Okay, so if it's convergent, you have a value for me that it converges to. 1. Okay, so these would be correct. Can you give me any arguments as to why this is the case?
I'm guessing because, so it starts at 1/2, that's half.
Yeah.
And the next one's going to add another half.
Half of what?
1/2. Which is
Yeah, half of the, okay, so this is a good argument. So I'm going to start it like this. So you guys are basically saying that this is equal to 1. There is a way that we can look at this, right? So here is the unit square. What's the area of the unit square? What is the area of the unit square? 1. Okay, so if I cut this in half, what's the area of this half?
1/2.
1/2. Okay, so that should be a half, yeah? If I cut that in half, this is going to be a quarter. If I cut this in half, it's going to be an eighth. But what do you notice? A half, a quarter, an eighth. Each number is half of the number before. So I can actually just continue, right? So the next number in this series is going to be a 16th, which is half of an eighth. Then the next one is going to be 1/32nd, right? And then in here, and then in here, and then in here, and then in here. It's obvious that by the end of this procedure, we're going to cover all of these square in the limit, if I use an infinite amount of these. Would you accept that as sort of an argument as to why this goes to 1? I'm going to give you an arithmetic one, which is probably the one that you're most comfortable with, but that's a neat geometric way of thinking about it. It's like this argument when you throw a ball against the wall. I don't know if you've ever heard it. The ball has to travel half the distance to the wall, and the remaining half of the distance, and the remaining half of the distance, and the remaining half of the distance. In the limit, the ball's going to hit the wall. That's sort of like this version of that if you're standing 1 meter away from the wall, of the wall.
Well, can't you like pick any shape and then I can cut it to half and half and half of a half and half?
Well, no, because this is a very particular shape because the area is 1. If I take half of the circle, you're going to have pi r as your area.
So if I use that explanation, wouldn't my answer be whatever the value there is?
No, because you're converging to 1.
No, I know that. That I understand.
No.
I'm just saying
1
that's-
half is not, it's half of the square, but also half the area. Like the original thing was 1. You want to start with a circle, your original thing is going to be pi r.
I know, but you start with 1 because you know the answer is 1.
Yes.
Yes, so what if you didn't know the answer?
Well, I don't know. Then you have to do something different.
Okay,
Right.
That's what I'm saying.
But the original question, can I start with any shape? Obviously, no. Right?
What if pi r equals 1?
Well, pi r doesn't equal 1.
What if it's pi 1/3?
What-
You're saying, what if I started with a shape whose area was 1? Yeah, it would work. Right? But then you have to make sure to cut it in half every time, which, right? There's no, anyways, this is just a neat observation. There are many other ways of doing this. Okay, so this was actually an example of something called the geometric sequence, or geometric series. So a geometric series is one that looks like this. It's the sum from k, this is important by the way, k equals 0. And I like writing it like this. I put the constant out here. Actually, I don't even really care about the constant. If you have r to the power of k, this is equal to 1/1 minus r, provided r is a fraction. Negative or positive. Doesn't really matter. Okay, so using this, what was the sum of that going to be? Can we use this equation on that?
It'd be 1/1 minus 2.
Okay, so for this, what do we first have to notice? Yes, sir.
It's actually 1/2 to the k, so you can say r is 1/2.
That's the second thing we have to notice, I think.
Oh, they don't start the same.
It's the first warning I gave you. Okay, so you got to be very careful about this. Okay, so we have to somehow re-index this. So if we start from 0, so how I re-index, especially when we only want to move from 0 to 1 or from 1 to 0, I just ask myself, what should the first term be? And that usually does it. So the first term here is a half. So the first term I have to have here is a half. And then I can multiply by 1 over 2 to the k. That's going to work. So for k equals 0, it's a half. The next one is going to be a quarter. So the first one here is a half. The next one is a quarter. So these two sums are going to be equivalent. This means that this is a half. K equals 0 to infinity of, I'm going to take your observation now. This is a half to the k, which is equal to 1/2, 1 over 1 minus a half, which is 1. Okay, so you don't always have to make these neat geometric observations to find these sums. But don't you think it's sort of curious how I gave you a geometric argument for this, and it's called the geometric series? Right? This is sort of the general observation about series that behave like this. These are going to be easy marks on your final. Many of you are going to cark it by not looking at the index. So I'm warning you now. Be aware of the index, or you're going to sacrifice easy marks on your test. Because these multiple choice questions, they're not going to be flexible. Okay, let's prove this. I actually kind of screwed this up. This isn't really a definition. This is a definition. This is called the geometric series. This is a theorem. I shouldn't have really written them at the same time. Right, so the geometric series is this, and like this actually, this equality is given by a theorem. And then let's prove that theorem. Right, basically that the sum of rk is equal to 1 over 1 minus r when r is less than 1. Do I actually have a proof for this? No, I don't. No, I don't. Sorry, guys. You can still use it, but I'm going to prove it. I have to prove something else. Okay, so let's look at this. Here's the theorem. This sum from k equals 1 to infinity of c times r to the n is equal to c over 1 minus r, which is convergent when r is less than 1. I am actually proving that. I'm losing my mind today. Okay, so let's prove this. It's actually not that bad. So recall at the beginning of class that I actually defined this, the nth partial sum. We're going to use that now. So what's the nth partial sum of this? That is the first n terms from here. That's going to be c. Did I start from 1? No, I got to start from, that should be a 0. That's going to be c r0 plus c r1 plus c r2, and so on up to n. Okay. Now what I can do is I can multiply both sides by r. I'm going to multiply both sides by r. You're going to get r Sn here. And then here, all of the exponents are just going to go up by 1. Okay, now, so we have Sn is equal to this, and r times Sn is equal to this. What happens then if I take Sn and I subtract r times Sn? So Sn minus r Sn is equal to what? Well, let's just pick these things off term by term. You're going to get c r0 minus c r1 plus c r1 minus c r squared plus c r squared plus minus CR to the n plus 1. I think I'm actually missing an n plus 1 there. Okay, so what happens?
They cancel out.
Yeah, I got a lot of cancellations. So this ends up being CR naught minus CRn plus 1. Okay? Which means that Sn, the nth partial sum, 1 minus R, I just factored that, is equal to, I'm going to factor out the C, and you're going to get 1 minus R to the n plus 1, which means that S of n, the nth partial sum, is C 1 minus Rn plus 1 over 1 minus R. Okay, so this actually is a closed form which is going to give you the partial sum of a geometric series for the first n terms. Now, recall, we have R is less than 1 in its absolute value. What does this mean about the limit of n goes to infinity here of that partial sum?
Approach 0.
What approaches 0?
The value, since R is smaller than 1, it's a fraction.
Yeah. So R is a fraction, right? So let's imagine a fraction in our mind, a third. If I multiply a third by itself, you get a 9th. It's getting smaller. If I multiply by a third again, you get a 27th, even smaller. Any proper fraction, right, that is to say a fraction that's less than 1, taken to powers is decreasing. Thereby, the limit of this is going to go to 0 in the limit. So what are we left with? Well, C over 1 minus R. Okay, that's exactly what I told you up there, except it's scaled by C. Right, just multiply that thing up there by C and you end up getting this. So it's not actually that difficult to prove that these geometric series converge to this in their limit. Okay, so I'm going to give you something to do while I wipe the boards. Please go ahead and compute for me. Sum k equals 1 to infinity of 1/3 to the k plus 1. So we got to do two things. Determine that it's a geometric series in the appropriate form, and then apply the definition / theorem that we have up there. Can I wipe these boards?
Wait, so R has to be less than.
No one's shaking their head, so yeah, at least be friendly and start from the beginning.
Every time R is less than 1. So it's always wait, this one, why is it less than
I'll make a lap. How can an absolute something be less than 0? Did I write 0? Why not 1? Why did you say something?
Because I don't know.
There's only one number whose absolute value is less than 0. No, there is no number whose number.
Because it's absolute
If I wrote r, the absolute value of r is less than 0, it's 1. I meant to write the absolute value of r is less than 1. There is no number whose absolute value is less than 0. It'd be pretty boring if I give you an equation that never applied in any situation. So yeah, so usually just I just prefer taking the constant out. So that's why I give the geometric sum.
No, it works. So it works. So it works.
So there's two things you have to do. The first thing I would do is reindex it.
So it doesn't apply, but it's still some.
Just distribute it.
Is it?
First term here is 9. Your first term is 9.
You have to change the index. Because you have to change it to the original equation, which was infinite sum from k equals 0 to infinity of r.
That's fine.
Right? So then we change it, and then you multiply them together to get the new index. To get the new index, and then well, we multiply 5 times to get the new index, so that's what I have to do here. And then I don't know, what do we do now?
That means that this is the series. That means that it's one of the
Pre-learning. And I learned the entire thing.
you can just take it out. It's going to be the same no matter what.
It's like so lit.
To the one.
Jens,
And
how
then
you go?
multiply by one.
That's a good place to start.
So plug in 0 in
Because that's what the first term
Plug in
is.
0 in here.
Okay, so if I want to start at 0,
Change 1 over 9. Plug in 0 in here.
yeah, I don't know why you changed that to 9. It's just because you 1 over 3. So this is, what you wrote here is this.
It's not fair.
You wrote this, 1 over 3 squared, with a k plus 1, which is, what was the initial basically 2 k plus 2.
That was the initial.
No, I know.
So re-index, yeah, so
That's
we
it.
just need a
I just had to write it.
So we're third index, so how are we gonna try it? So 1 gives me 9, 2 gives you 27. Here, 0 gives me, so 1 gives you 27. Okay, so of course, everything else is going to sort of match up together. But it's still well, basically, I want it as like, you always try to get something as a fraction to the exponent.
Because if it's going to be that means that it's going to be k 0 plus 1 plus 2 plus 3 plus 4.
I understand, but
You could say
how show that this?
Divergent?
I'm done. Yeah, okay, that's perfect so far. Thank you. How are you going? Well, what you wrote here is 1 to the power of k plus 1 over 9. So this is not correct. Well, your brackets are only in the numerator. That's totally different. You bracketed the top. You're saying take the exponent to the numerator, which is 1. You just had a 9. I know you probably wanted it in that, but that's not what you wrote. Good hair. Yeah. Okay, tell me why. Yeah, the first thing I have to do is okay, I'll show you. It's actually less complicated than we think. Okay, what's the answer?
1 over 6.
1 over 6? Okay, so what's the first step here? I go from k equals 1 to infinity of 1/3 k plus 1. Okay, so what's the rule that we have? We have that the sum from k equals 0 to infinity of r to the k is equal to 1 over 1 minus r when r is less than 1. Let's just keep this in the back of our mind. So what's the first thing that I have to do here, right?
Change the index.
Okay, we have to change the index. So I want to start from 0 to infinity. So there's two ways you can think about this. I actually did the substitution k gets k minus 1. Or you can just ask yourself what the first and second term is. So the first term here is going to be what? A 9th? The second term is going to be a 27th. So the first and second terms here should be the same. So we're going to have a third. So to get a 9th as my first summand, that's a plus 2. All right, the next thing is going to give me a 27th. Okay, so can I finish yet?
Well, you want to get rid of the k plus 2.
Yeah, exactly. So I just want to sort of emphasize this. This is a k. This is a k equals 0. This equation only works in precisely this form. Precisely this form. Okay? We're not quite there yet. Right? Because this is not k. So how can I get rid of two of the k's up there? It's actually easier than you may think. Whoops. 0. I'm just going to remove 1 over 3 squared. Everyone believe that step? It's just high school arithmetic. All right, so what does this mean? This means that we have 1/9 sum k equals 0 to infinity of 1/3 to the k. This now is a form where we can attack it. It's a geometric sum. So you get 1/9, 1 over 1 minus a third. This is going to be 2/3 on the bottom. So 2/3, so it's going to be 3/2 times a 9th is going to be a 6th, I think. Who else got a 6th? Okay, good.
That's all the confirmation. That's all the confirmation.
Well, at least one of you need to get a 6. Any questions? Any questions on this? Okay, let's move on then. Or you guys want to try one more? What time is it? We got an hour. Yeah, I'll give you guys one more. Let's do one more. Okay, so here's another example for you guys. Give it a crack. Sum k equals 0 to infinity. Minus 1 to the n. 5. 4 over n. You don't need SN for this. Why are you bringing in partial sums? You're just pretending to be me. Yeah. Yeah.
Can you say Patrick? Okay. No, can you see what you need to do? I think we should do negative 1 over 4 to the power of n.
Oh, sure. Why don't you take 2 of them? It'll be 5 over 4. Yeah, your way takes twice as long. How is that conceptually easier?
Oh wait, it's not. I just realized it's not the same. Did you do that?
Oh, but you're correcting based on knowing what
We can't get a value for n.
properly. You're not making the right. You're not going to know anything from the exam. You're going to do this again. There's no way. It's n.
Oh, you should have that. It's an n.
That's not the
There's
no,
2.
that's not the right hand. No, he writes N's like that. Yeah.
Yeah, hold up 1/2.
You can't take any value for n.
I need to get rid of 3 of them. So don't just copy what
So you mean it's n equals 0.
The objective was to get
Well, if it is,
Let us
the
pretend
objective
that
here is the same, get a case.
But then that goes
Okay. Process is that
Stay
not
at
equal 1
the end.
no,
Like,
that's
you can do it on
many
purpose.
things I can see. As many things out of the I need to get a k. Because in the end, t equals 0, nothing, and r to the k. So half it needs to be that.
Almost.
Negative 1 means you can and minus 2. You would have had to introduce 2 extra.
If this form is gonna be
Then you would have had to multiply by 9.
Wait, you tell me one of
It won't do it. It won't do it. No,
Well, remember, it's
cancel things out.
objective. You're trying to figure out what the objective was. Copy the objective.
Okay, then have a negative 1 to have a negative 1 to the end.
That's always something I'm just trying to accomplish.
Did you need to have 2 different variables?
And what do you mean? Oh, yeah, sorry, that should be an S. This would be easy if this was a
Test,
K.
how are we supposed to know that?
Yeah, or you want to be like, sorry.
Raise your hand and ask clarification. Right? And then when you start doing all of your work perfectly, then you can teach me how to do it. To work without ever making a mistake.
Well, we can't identify.
So what do you teach?
Huh?
What other courses do you teach?
At the moment?
Or no, next year. Fall.
Introduction to Computer Science, that's CS 108. This again,
Unfortunately.
and then in the following term, some weird like writing course for the computer scientists.
Oh,
And 148.
Is that the communications one?
Yeah.
Okay, I'm taking
Oh, I occasionally get visitors. Everyone wants to bring their friend to see Professor Berman.
It's the best class. Yeah, bro. It's the best class.
So what are we gonna do time for?
Why can't I just this is
You can't bring up the negative.
make the n here in specific.
The negative's in the brown. You can't
The only thing that's the only thing that negatives
Do them separately.
What if
Define the sums and then add them.
I can't use that.
You should properties are
That's not the same.
Because it's not -1/4. It's not how it works.
You cannot do them separately. They're not being added. They're being I cannot just add something else. I don't see why we can't do -1 to the end times.
Oh, yo, it's -1/4.
How did I not do that?
It's -1/4.
So that's what I said.
Okay, you're right. But I get 1/4 the end.
It's so annoying. What? Okay,
And it
go.
works because R is left and
Wait, what?
absolute value of R is
So
less
it-
than 1/2. If absolute value of R is greater than 1/2.
K, this K, we have to substitute K. Yes.
Bro, mine was like that. It was like 7 long and like 30. But each multiplication like on the priority. Bro, I was like sad studying. No. I studied like a week every
We
day.
need like 2, 3 weeks.
Yeah.
Sequence system.
No, this after this one, the next one. When we use like randomness.
Right? They're like, I don't recommend doing it. You're gonna screw it up. I screwed it up. It's a fucking. Well, you just did that. I don't know why you did it. What's your Yeah, I understand. In order to accomplish what you're
Everything's wrong. You just multiply.
That's usually the error.
It's low.
I know it's doing this.
Oh yeah, okay, no, I
You match the this video. Anyone have an answer for me?
This.
You say 4?
Yes, sir.
How much of your grade do you want to gamble?
All of it. The whole, my whole grade.
The whole grade.
It's not much, so he doesn't really care.
Oh,
You should have gambled.
okay. I did gamble.
What do we actually have?
You should have got it in writing.
I pulled up.
Oh, yeah.
Okay, so let's just do this one. So what? This is n equals 0 to infinity of -1 and 5. God damn it. Over 4 to the n. Okay, so my strategy when doing these series is, and when I do integrals, if you haven't noticed, is I usually just remove all the constants first. Right, so I have, I'm just going to take out the 5. And then you get sum n equals 0 to infinity. And I guess what you're left with is minus a quarter to the n. Is that what everyone got?
Yes.
And then this one is easy, right? So this is just 5 times 1 over 1 minus a quarter. This is 3/4. So 3/4 becomes 4/3. Wait. Oh, yes, 1 minus a quarter. Thank you. That's the lesson I'm trying to teach. That this could be negative, and it will still work. Right, so you get 1 over 1 minus a quarter, which is 5/4, which cancels with that, which makes it a 4. Okay. I'm going to give you another one that's kind of fun. What fraction has decimal expansion? (5.23232323) repeating. Am I losing you guys? Because this is going to be on your test, and it's going to be heavily weighted, right? So. Well, not this particularly, but this topic is going to constitute 50% of your final. Right, so maybe you should pay attention. Your friend is more attentive than you are. He's not even in the class.
We strive to-
What fraction gives me the decimal expansion 5.2323232323, and so on? Put on your thinking caps. You do have the tools to solve this. Why don't you try writing out a series who will give you that decimal approximation? 5.1 is 5 plus a tenth. 5.11 is 5 plus a tenth plus 100. That's a clue. She's giving me the death eyes. I've seen that before. I am not impressed.
Isn't it 5 plus 2, 3 to the negative? Okay. Oh wait, 5 plus 2, 2, 3.
Give you guys a couple minutes. Yeah, guessing is always the first thing that you
I'm
should
thinking
do.
it could be 5 plus 0.23 to the negative k. Because then it would be 23 plus 0.023.
You're almost there, but 0.23 to the k isn't going to give you what you're thinking.
Negative k, sorry.
That's going to be even worse because now you're dividing, right?
Oh, true.
That's close.
I'll take the 5 as a constant.
All right, first hint. First hint.
Oh, over 10. 10 to the k.
That's not a hint, that's the answer.
This is a fraction? It's news to me, right? In fact, you can use these geometric sums to backwards engineer any fraction to any decimal that you want. This is called rational reconstruction. It's interesting.
Yeah, that's the answer.
Ready to give you this thing?
Or sorry. No, like this. Yeah, I know.
I'll bring you a sticker.
23
Be surprised how much that's like.
plus 5.
You're adults too.
So it has to be 5 to the
Makes me feel like
I always scratch this sticker. It's working.
5 plus 23.
Start at 5. No, you're using the index. Then you're at a big one. This K.
I want this
And
one.
designate.
You just do the denominator. Yeah, I did. No, it does not. Literally, this makes more sense.
Then the only thing you would ever be able to add is 1. Sequences is there's a kind of a very special notation that if you make K is an index variable. Like weird science kids understand. We often
This is a mixed array.
and add up the content. Greater index. As soon as you start to create Okay, next hint, next hint. This is going to be 5 plus sum k equals, I'm going to say 1 to infinity of 23 over, oh actually no, I need to start from, no, I need to start from 1. 100 to the k. Okay, so now I think at this point this is giving you the answer. So be careful, you're going to have to do a re-indexing. And now tell me what the fraction ends up being. And we'll make one more lap. Yeah.
Go back and see
No, 5 plus.
It's 23 over 100 is 0.23. So 5 plus 0.23 is 5.23. That second line is the first one.
Yeah, I know.
Okay.
I know.
So the
But
get from
it's
1 to 2 should.
No, it's getting to the next step.
I just wrote the.
Oh, yeah, I know. Right after what you just wrote.
Yeah.
So the problem is still getting to the next step.
So the next step, and I'm not trying to be facetious about this, it's the same thing. I'm just utilizing the sigma notation. Right? Like we should be used to this. We use sigma so much during Riemann sums.
Yeah.
And so I'm just saying, look, I'm just writing it down using sigma. Those three things are on the order. There's no strategy for moving between one and the other. I'm just like, yes, I'm summing up an infinite amount of stuff. I'm just going to write it now using this new notation. It's not. I'm not solving any. It's just genuinely just rewriting it. There's got to be comfortable converting between line 2 and line 3. The strategy is just this is how we write stuff. If we're adding a bunch of stuff together, you could just try unpacking it. So it's going to be k equals 1. That's 23 over 100. K equals 2. That's 23 over 100 squared. You just got to sort of work with each other a little bit. You got to get used to it. If you buy left, fraction.
Yeah.
Oh, you usually expand it like
I wrote the sum. Don't forget to put dots. You're adding way more than 4 things.
You can make like terms and then add it and then so 5 over 90. No, 5 times 5 take like terms.
I know what you're saying.
No, 49, so 49.
Well, this isn't my.
He's just doing this one. It's not how you do it.
Okay. First one.
Okay, yours was like.
Your first one here.
Plus 23.
Oh, plus 20. You're gonna say that's fine. You gotta imagine these figures like that. You wrote it all out. And then it becomes wealthy. Factors. Don't treat this as I don't want to write down. What's the you want to read all of this not based on your first year. Just because 99 million is a little white train idea. Yeah, okay. Yes, yes.
That's 31 centimeters. That's so cool.
Anything else?
Oh, yeah, I can delete those apps.
Okay, so 5 times 9.
That's what we need.
Why would you say it's too hard?
I don't know, it's probably just because it's simple. I'm like getting tricked by myself, I don't know.
Why would you expect it to be simple?
I don't know.
Hey, fractions compared to these integrals, that's no, she didn't learn to omega rate.
That's 16. Whatever it is.
Who has an answer?
Yes, miss.
We got 518 over 99.
That's 518, but that's what both of you. Or you were in, I thought you were in a contest to see who was right.
Oh, no.
Teamwork.
I have 518 over 99. All right, let's try working this out. So I'm going to continue from here. So we have 5 plus sum k equals 1 to infinity of 23 over 100 to the k. So I'm just going to show you how I do it. It's 5 plus. I'm going to remove all these constants. So I got to go from 1 to infinity of 1 over 100 to the k. I want this to start from 0. So actually what I'm going to do is just factor out 100. Okay? This is going to start from 0 now to infinity of 1 over 100 to the k. And I'm just going to check the first couple terms, because usually that's sufficient. So the first term coming out of here is going to be 1 over 100 times 23. So the first term should be 23 over 100. For here, if I put in a 0, this becomes 1. And this becomes 23 over 100. So that's the first term. We're good. Second term here should be 23 over 100 squared. So the second term here comes from k equals 1. So that gives us 100 here. 100 squared, 23. That seems fine. Now I'm going to use the formula for a geometric sum. This is going to be 5 plus 23 over 100 times 1 over 1 minus 100. This is going to be 5 plus 23 over 100 times 100 over 99. You get some nice cancellations there. So you end up getting 5 times 99 plus 23 over 99. I'm going to show you, so since I was removed, like my calculator was stolen from me very early. So how do you do this? Well, this is 5 times 100 minus 5. Right?
Oh, yeah.
So that's 496 plus 23 over 99, which is going to be 500, no, I don't trust myself, 18. Hold on, I screwed something up. This should be a 5, 495. 518 over 99. Okay, who has a calculator? Legit all of you, right? 518 over 99, please. Anyone?
5.2323.
It's right.
5.23232. Okay, great. See, we backwards engineered a fraction from its decimal expansion, which is pretty cool from a computational standpoint. Okay, telescoping series. So you know how telescopes could do this? Right? You can like compress them, expand them. That's where it gets its name. These aren't series that you look at really closely. I guess that will be a microscoping series. Any case, insert preferred dad joke into this part. So a telescoping series is a series where most, it's not very, I don't know, precise, but most terms cancel, making the sum easy to find. Okay, so we actually had an example of a telescoping series the other day, and that was this guy. Right, the sum k equals 1 to infinity of 1 over k plus 1. We learned this could be written like this. 1 over k minus 1 over k plus 1. And then when we worked out a few terms, we saw that we're getting sums like 1 over 1 minus a half, plus a half minus 1 over 3, plus a third minus a quarter, and so on. Right? So what you end up doing is canceling most of these terms. And what you're left with should be 1 over, minus 1 over k plus 1, and so on. But the point is you get like a closed form for the partial sum. So a telescoping sum is one where this happens. So you may have to sometimes just be clever enough to notice that you're going to get these cancellations. So try, like, the sum being telescoping is something that you're going to have to account for when we're asking you to resolve these type of questions. It's just like integration. I can't tell you ahead of time which technique is going to work. I can simply give you tools to put into your toolbox, which you can then use when given one of these problems. Right? So telescoping is one of them. So the next thing we're going to care about is divergence testing. That is to say, so let's just take a look at this. Suppose we want to do this sum, the sum of ak from k equals 0 to infinity. And suppose further that the limit of k equals infinity of ak is equal to L, which is convergent, less than infinity, but not equal to 0. Right, and let's say that it's, less than infinity is not equal to 0 and divergent, let's say. Okay, what can we tell about this sum if I'm telling you that the summons eventually limit to something non-zero? Just think for a bit. I can walk you through it. Okay? So if I start writing out terms of that, right, so you're going to have the first term, the second term, and so on. Eventually, these summons are going to limit to L. And you're just going to have you're eventually going to hit this. So what happens to the sum?
Infinity?
Yeah, it diverges. Right? If these aren't 0, then eventually you're going to add up to infinity. Does that make sense? So this is divergent. Now we're getting into where you were getting. But you had it a little bit off. Every time.
What if L is 0?
Then I can't make this claim.
So, like, what happens?
Well, we have to different. Like I'm saying, let's consider that we're in this situation. I'm going to tell you something about it. And you're saying, well, what happens if we're not in that situation? The answer to that is that I have to tell you a bunch of different stuff, right? So. Okay, so notice if the individual terms aren't decreasing to 0, then you are assured that your sum is going to add to infinity. Right? Because so suppose an goes to 1, then at some point in your series you're going to have 1 plus 1 plus 1 plus 1 plus 1 forever. Okay, so it seems intuitively clear that in order for our sums to diverge, we at least need the terms themselves to limit to 0. If they don't limit to 0, I can always write plus L plus L plus L an indefinite amount of times. Right? L has to be 0. These sequences have to go to 0 in order for their series to converge. Okay, so I'm gonna codify that into a statement, and we have to be very careful about inferences here because people make this mistake all the time. Okay. We know if this sum is convergent, then limit of ak as k goes to infinity is 0. This is called the divergence test, nth divergence test. Who remembers what the contrapositive is? Well, here's a statement of logic. This is an inference. There's going to be the opposite of this inference. So there's we can also have the negative of this statement. All right. If A implies B, then we also have not B implies not A. Okay, that may not make sense, but how about this? If it is rainy, then it is cloudy. And from this we can say if it's not cloudy, then it's not rainy. So this is an inference statement. This is the contrapositive. The common mistake made by humans is to assume from here that you get this. This is not the case. That's not the contrapositive. You can intuit that this isn't true. It could be cloudy and not rainy, but it can never be rainy and not cloudy. And it can never be raining if it's not cloudy. I know I just said the same thing twice, but these are equivalent statements. That's my point, right? So what's the equivalent statement here? Limit of k goes to infinity of ak isn't 0 implies this sum diverges. What don't we have? We don't have that if the sequence goes to 0, then this is convergent. We don't have that. Right? So don't make that assumption. It's not true. Right? So for one, I'm going to give you an example. We're going to learn about this next class. Okay. Okay. The sum k equals 0 to infinity of 1 over k, which is 1 plus a half plus a third. One day I'm going to murder whoever makes this chalk. And I mean that. I really do mean that, YouTube. You can report me. Okay. 1 plus a half plus a third plus a quarter plus a fifth, right? So ak here is 1 over k, yeah? The limit of k goes to infinity of 1 over k is what? Are you kidding me? Right?
Oh, I was looking at the one above.
Yeah.
0.
0, yeah. Okay. So the sequence, right? So the sequence, so these things are getting smaller. They indeed go to 0, but this is divergent. I can't show you why yet. We're going to do that tomorrow. This is a sequence called the harmonic series. Okay, but this is the de facto example of something with terms that are trending to 0, but that still nonetheless diverge in their series. So be careful. So if there's a multiple choice question, which I fashion into a true-false one that says, you are summing a sequence which trends to 0. Does that sequence converge? Or does that series converge? The answer is no, not necessarily. And if I asked you for an example, you would give me the harmonic series. Okay. So I'm going to give you an example that is not the harmonic series.
Professor,
Yes.
what would that approach though? What approach do?
What would this approach?
Yeah. It's one plus.
Someone in class, I just told you this series is divergent, so what would it approach?
Oh my god, what did that approach anything?
Doesn't approach 0 but not pass it?
No.
Okay, what are you talking? Okay,
No, no.
first you have to tell me what it is we're talking about
No, I
approaching.
see why I'm wrong. I thought it approaches something, but that means
The series is divergent. It approaches infinity, right? Not 2. I don't know where you're getting this 2 from.
Okay.
He mixed it up with like the beginning when
Yeah.
we're doing the square, and he's like, oh, 1 plus the whole
Plus
square.
that one.
Yeah, it turns out if I square this,
Yeah.
then what does it become? Yeah, but specific. It's a geometric series if I square it. Right. Guys, we just did that. I just taught you that.
Oh, yeah, 'cause
This is a geometric series if I like put that to oh, I guess that can't be K. I redact that. Bad me. That's not a geometric series. You're all forgiven for looking at me confused, right? Again, that was just one of my secret tests. Yes, always a secret test. Okay, so let us try an example which you should have the ability to attack. So tell me if this converges or diverges or not. So specifically, what does the nth divergence test tell us about this sum? Hints. This is a telescoping series. Try to work it out. So what's the limit? So this is the summed. What's the limit as k goes to infinity of this?
1.
Ln of 1, which is
0.
0. Okay? So we have here that ak is equal to ln of k plus 2 over k plus 1, which implies that the limit as k goes to infinity of ak is 0. Okay, so the terms are getting to 0, and we're adding them. Is this divergent or convergent? So can I conclude from this that it's convergent?
Yes.
No!
Why? Oh my god.
Because of that.
No, I went through great pains to tell you that you can't conclude anything from this.
I'm just pissing you off today.
Yes, you're very effectively,
That was
right?
his test, don't worry.
We gotta do the same.
Can't wait to mark those exams.
Testing your testing ability.
Oh, by the way, it's a different type of Scantron sheet that you may not be used to. So we're using a different piece of technology called like zip scan or something like that. So the Scantron sheet is like there's going to be a page with a bunch of bubbles you have to fill in. And you can do it with pencil, you can do it with pen, it doesn't matter with me. But you just have to do it accurately. I'm just going to point my phone at the page and it's going to scan the Scantron like that. So, but just be sure not to fill in 2 bubbles, because that automatically means it will be graded wrong. Right, so bring a pencil if you don't normally bring a pencil.
This movie's so old.
When you do, when you have lots of
Oh my god.
quotient divisions. Ln of A over B is ln A minus ln. Okay, so one hint. How can I decompose this? What is another way I can write this? And I'm not talking about the index. How can I decompose this? ln of A divided by B is ln of A minus ln B. Okay? So this actually is ln of K plus 2 minus ln of K plus 1. Now, very obviously, you're going to get some telescoping behavior. Right? Try to suss out what terms are left over once you do all the cancellation. Okay, so it's going to work it out. So you get this. All right, so the first thing I can do is just distribute out the ln. This is going to be ln of k plus 2 minus ln of k plus 1. If I copied everything correctly. Yes. Okay, so let's just look at what happens here. I'm just going to write out some of the summons. You get ln of 3 minus ln of 2 plus ln of 3 minus ln 4 plus ln 5 minus ln 4. Hold on, what is going on here? Where's my telescoping? What are we left with? Am I making a mistake?
So is there any C that's K plus 2 or just with ln? So you can split it to minus and because it's a division of two terms.
Someone help me. Oh, yeah, here's my mistake. Here's my mistake. That's a ln 2. Wait, hold on. Okay, so for 1, this is 3 and 2. For 2, this is 3 and 2. For 3, this should be 4 and 3. Aha. And so on. And I think the last one is going to be ln of k plus 2 minus ln of k plus 1. So what cancellations do we get here? You get ln 3 cancels with ln 3. Yep. We can do it. I'm gonna try again. I don't give up. Okay, so we get ln 3 minus ln 2 plus ln 4 minus ln 3 plus ln 5 minus ln 4, and then a bunch of stuff plus ln k plus 2 minus ln of k plus 1. Okay, so what cancellations do we get? Okay, ln 3, ln 3, ln 4, ln 4. This 5 is going to cancel eventually, and I think we're going to end up canceling this negative, or that ln. So we're going to end up with the kth partial sum is ln k plus 2 minus ln 2, which means that the infinite sum is when I take this to infinity of sk is going to be, well, infinity. So this is divergent. Okay, so here's an example of a series whose summands are tending to 0, but whose sum is nonetheless divergent. And that's where we'll stop today. There's some exercises up there for you. I'm going to add a few more, but you are released. Go into the world.
I remember the web work.